In this video, I'd like to talk about Chapter 12.6, a model for chemical kinetics, namely the collision model. So, why is the reaction rate usually, in most cases, dependent upon the concentration of reactants? Well, as the concentration of reactants decreases, there are fewer collisions between the reactant molecules, so the reaction occurs more slowly. And that basically is the collision model. It's a very simple concept, and that is, in order for molecules to react, they must collide with one another, either in the gas phase or the solution phase. So, how does the rate of reaction, actually the rate constant, depends upon temperature? Well, if you were to carry out an experiment in which you measure the rate constant for a reaction, K, at a series of temperatures, and graph them, you would see, interestingly, that the rate constant actually increases exponentially with temperature. And we can explain that through the kinetic molecular theory, which says that as the temperature increases, the velocity of the particles increase, therefore the frequency of collisions, as well as the kinetic energy with which the collisions between the particles occur, both increase. And you can actually calculate the collision frequency. It turns out, though, that the actual rate of reaction is much less than the collision frequency. That is, only a small fraction of the collisions actually result in reaction. Why would that be? Well, there are a number of factors. This was first explained in the late 1800s by the Swedish scientist Svante Arrhenius, whose name probably sounds familiar to you. He proposed that when two molecules collide, they must do so with a minimum kinetic energy in order to undergo reaction. And that minimum kinetic energy of collision he called the activation energy. Let's see what this looks like graphically. We'll consider the reaction of two molecules of nitrosyl bromide to form two molecules of nitrogen monoxide and one molecule of bromine, all in the gas phase. We can draw a potential energy diagram, sometimes also called a reaction profile, that looks something like this. We graph reaction progress on the x-axis and potential energy on the y-axis. We show the potential energy of the reactants and products. So here we have our two molecules of nitrosyl bromide. Here we have our two molecules of nitrogen monoxide and one molecule of Br2. If I were to draw a dotted line here and draw an arrow going up to the peak of the curve, this corresponds to what's called the transition state or the activated complex. And that is simply the arrangement of atoms that corresponds to the maximum potential energy. The difference in potential energy between the reactants and the transition state is the activation energy, E sub A. Okay? So Svante says in order for reaction to take place, the kinetic energy with which the collisions occur must be greater than or equal to the activation energy. And those collisions that occur with sufficient energy to achieve this transition state can then continue down the hill and form the products. However, those that occur with collisions less than the activation energy, that is, the collisions occur with kinetic energy lower than the activation energy, they do not proceed to the products, they simply revert back to the reactants. So, in order to react, the molecules must collide with sufficient energy. Once again, the kinetic energy of the collision of the reactant molecules must be greater than or equal to the activation energy for that reaction. They also have to collide with the proper orientation. This is kind of important. So if we consider our reaction, we realize that in order for this reaction to take place, we must break two bromine-nitrogen bonds and form a bromine-bromine bond. So let's consider some possible collision orientations. If the molecules collide in this direction, will reaction take place? Yes, because that permits bromine-bromine bond formation. If molecules collide with this orientation, will that allow the reaction to take place? Yes, because that also allows for bromine-bromine bond formation. What if they collide with this orientation? Will that allow the reaction to take place? No, it will not, because bromine-bromine bond formation cannot occur. So we need to take into consideration not only the activation energy, but the orientation. So Arrhenius put all of this together in what is known as the Arrhenius equation, which tells how the rate constant depends upon temperature and other factors, as well as the activation energy. And his original derivation of the Arrhenius equation looks like this. K, the rate constant, equals Z times P times E raised to the power of the negative activation energy over RT. Z is the collision frequency, and P is the steric factor, which is basically the fraction of collisions that result in reaction. These two were combined into a single constant called A, the collision or pre-exponential factor, which in Arrhenius' theory was assumed to be temperature independent. So now we can see how the rate constant depends upon temperature. In the exponential term, we have the negative activation energy over RT. As temperature increases, the exponential term becomes less negative, therefore the rate constant increases. Okay? And we can imagine that by looking at what's called a distribution curve. On this graph, we have the fraction of collisions that occur with a specified energy on the y-axis as a function of energy. If we look at the T1 graph, okay, which is the blue line, we see that very few collisions occur with low energy, very few collisions occur with high energy. Most of them occur with an energy right around here. Okay? Now, on the x-axis, you see the activation energy. The area underneath the curve, shaded dark blue, represents the fraction of collisions that occur with an energy equal to or greater than the activation energy, and therefore result in reaction. So as you can see, most collisions don't result in reaction, only a few do. But as you increase temperature from T1 to T2, now look at the red curve, you see that the distribution curve is shifted towards higher energy, okay? And that kind of makes sense because at a higher temperature, the particles are moving with greater kinetic energy, so they'll collide with greater energy. And now if you look at the area underneath the curve, you'll see that it's increased. Okay, so at higher temperature, the fraction of collisions that occur with a kinetic energy greater than or equal to the activation energy increases, therefore the rate constant increases. So that explains why rate constants increase with temperature. Now, we are not going to do any calculations involving the Arrhenius equation, unfortunately, because it was removed from the AP curriculum a couple of years ago. Very unfortunate. But if you wanted to determine the activation energy, here's a cool graphical way to do it. If you take the natural logarithm of the Arrhenius equation and write it in logarithmic form, you will see this is of the form y equals mx plus b. So graphing natural log of the rate constant as a function of 1 over temperature in reciprocal Kelvin will give you a straight line, the slope of which equals negative e sub a over r. That allows, I'm sorry, not t, because t is a variable, okay? And because activation energies obviously are always positive quantities, the slope of this graph will always be negative. So to calculate the activation energy, it would simply be negative r times the slope. So let's get some practice dealing with reaction profiles. So for the following reaction profile, indicate the positions of reactants and products, the activation energies of the forward and reverse reactions, and E sub A, pardon me, delta E for the reaction. So obviously early in the reaction, we have the reactants. Later in the reaction, we have the products. The activation energy of the forward reaction, so let me draw a dashed line here, okay, and one here as well. So this would correspond to the activation energy for the forward reaction, but the reverse reaction, going from products to reactants, I would need to show the energy required to go from products to the transition state. That would be the activation energy for the reverse reaction, and delta E would simply be the difference between the energy of the reactants and products. Okay. Now, what would a potential energy diagram for a two-step mechanism look like? The previous potential energy diagram or reaction profile clearly only involved a single elementary step. If there are two elementary steps, then there must be, obviously, two peaks. And it would look like this. Okay. So, to label this diagram, this would be the reactants, this would be the products. What do I call the thing that's formed after the first step and used up in the second step? That would be called an intermediate, which I will label as I. So here is the activation energy for the first step, EA1. Here is the activation energy for the second step. So the question arises, which step is the rate determining step and why? Well, if you think about it, you'll realize that the smaller the activation energy, the greater the rate constant, and correspondingly, the greater the activation energy, the smaller the rate constant. So first step must be rate determining step, and that is because it has a greater activation energy. Okay, and in our final video for this unit, our next video, we will talk about catalysis.